minus 3. Yep. Okay. So 189.22 power minus 6 plus 37.321 power minus 6 is equal to 226.541 times 10 to the power minus 6 meter cube. Okay. So 189.22 plus 37.321. 226.541. Okay. So finally, any questions from anyone so far? Okay, it's just plug. I mean, you have to be organized with the geometry, then you'll be fine. Okay. A lot of students make mistake about here. Okay. So this is the value we know. And then now it's time to plug everything in. Okay. So the shear stress will be equal to, so we are considering the 25 times 10 to the power of 3. That is the shear force, then 226.541, 226. Second moment of area will be equal to what? 40.9. And then the thickness given is 7.2 times 10 to the power minus 3. So this will be equal to 25 power of 3 times by 226.541 power minus 6 divided by 40.9 power minus 6 divided by 7.2 power minus 3. So it's equal to 19.232 times 10 to the power 6 Pascal. Okay. So this is just one of the shear force. Next, we are going to consider the Vx, which is equal to 16 times 10 to the power 3 Newton. Okay. So let me get the cross section over again. And we happen to be really, really lucky this time, because Vx is coming in this direction. Okay. And when we design the shear flow, at the center and over here, this is where our what? Element what? P is. Okay. So using thin wall analysis, all right. So we have the shear is equal to Vx over Iyy Qy divided by T. And when you look at Qy, it's equal to width times depth, and the Y bar is equal to what? Sorry, the X bar is equal to what? 0. So therefore, the shear is equal to 0, okay, due to the what? 16 times 10 to the power 3 Newton. Okay. So we only have one shear flow, or we only have one shear stress of 19.232. Okay. So finally, not finally, but the next thing we're going to do, we're going to construct the element. So we're going to do some construction of element. Yes. Say it again. Yep, it's also. What do you mean draw this on the shear force diagram? Nothing to do with shear, nothing to do with the shear force diagram. Shear force diagram, the force we have twice of, we have 16 kilonewton. It's because of the first moment of area is equal to 0. Okay. Now, so now we are going to draw element B. So this is our X. This is our Y. This is our Z. So this is where we're going to sketch our element. And we are aware that we have a compression coming down. This compression we calculated to be what? We have calculated the compression to be equal to 14.996. Okay, 14.996. If we were to construct the shear flow will do this, and then will go this direction. Yes or no? Okay. So you'll go into this direction. This is our shear flow. And if we were to look at our transformation, this is shear Z in the Y direction. This is shear Y. The shear flow is in the Z direction. So we can come back to here to calculate that we are calculating shear what? ZY, or YZ is the same. And this value will be equal to 19.332 times 10 to the power 6 what? Pascal. Okay. So that is our element what? D. Okay. So from last week, on Friday, we have sketched what? We have sketched element A. Okay, last week, we have sketched element A. Okay, so if I were to bring this across, okay, if we were to bring this across, hey, come on. Okay, so what we have over here is our element what? Our element A. And I want you to look at the shear stress value. Okay, I want you to look at the shear stress value. Can someone comment on the shear stress value relative to the normal stress for both elements? What you observe for element A, the shear stress value is very what? Low. Yes or no? If you look at element B, it's higher, right? Relative to the normal stress, right? Then the thing comes to your mind. So if you are a gadget from any other university, probably element A, you might be lucky. Because it's so small, right? You will not increase your maximum normal stress. But if you were to look at element B, if you don't calculate the shear stress, what happens? You grossly underestimated the what? The normal stress. Can you see where the problem is? When I finished my undergrad, I did not know how to calculate shear stress. I just put a factor of safety of 2, 3, 4. With what all of you have learned, you can be very, very what? Precise. But don't be too arrogant, yes or no? If you are good, be what? Something. Be clear. Okay? Now, question for you all. Which one has the maximum normal strength? Okay? Time down. Yeah. Can you tell? Both circles. You see the importance of both circles. Now you come down, not like, element 2, element B, higher shear stress, normal stress load. You have 50-50 this. Yes or no? Okay? So now we're going to do 2 things today, okay? The next example I'm going to give you is like crazy bombastic. It's crazy. Okay, it's not crazy. But for now, I'm going to introduce to you 3D mold circuit. Okay, and I'm going to show you 3D mold circuit. And as I say later on, probably on Wednesday, I'll start from 2D first, then I go 3D. But I want to show you what 3D most looks like. Okay? And this is the first time you have seen 3D motion. Okay? So what I'm not sure, we know that the normal stress is 29.658 for element 1, for element A. Yes or no? So the maximum stress will not be so far away from 29.1. 29.658. The only thing that we're not sure is the what? Is that element over there. Okay, element B. So let's focus on element B. So we know, just listen to me now, okay? We know that stress max for element A, stress max is approximately equal to 29.658 times 10 to the power 6 Pascal. Okay, approximately. Okay, if you ask me approximately, I think plus or minus 5%. Okay. This one, we are not sure. Okay, so now let's do 3D Mohs circle. Okay, very briefly. Don't panic if you like, what is this all about? Don't panic yet. Okay. Any idea when you should panic? Anyone? You only panic when I panic. Okay, if I don't panic, you don't what? You don't panic. Are we clear? When I say we are all going to die, we are all going to die. Okay, but if I don't say that, you're all fine. Right. So when we write this, so this is our Z. This is our Y. And this is our X. Okay. So what we know so far is stress X, stress Y, and stress Z. We know that stress Z is equal to minus 14.996 megapascal. And we know the rest are equal to what? 0. Before I go on, can you all make a guess? Okay, can you all make an intelligent guess? If this thing were to fail, which surface will fail? Anyone? Is it the one with the biggest face, or is it the horizontal face, or is it the vertical face? If this thing were to fail, where is it going to fail? By the way, this is outside the syllabus, but you have to know. Wait here. Anyone? Come on, look at how the structure is molded. How it feels. Have you all done labs yet in mechanical testing? No, not yet. Okay, good. Okay, because when I think you all have a mechanical testing lab where you pull samples, and you know where it will fail depending on where the load will apply. Where it will fail, regardless of normal stress or shear stress, is going to fail on this surface over here. And it's going to fail on this surface over here. Are we clear? That surface relative to the main structure is basically the top. It's not the top surface, but it's the horizontal orientation what? Okay. Fracture or occur. Okay. So from here, we are going to construct more circle on this. Okay. So we know that shear ZY is equal to shear YZ and is equal to positive 19.332 times 10 to the power 6 Pascal. Don't worry about positive and negative yet. I will teach you later. And we know that shear XY is equal to shear YX and they're all equal to 0. Shear XZ is equal to shear ZX and is all also equal to what? 0. Okay. So from here, we are going to label our surfaces. Okay. So this surface over here is our surface Z. This or point Z, this is our point X, and this is our point Y. Okay. So now we are going to construct 3D mole circle. Don't panic, 3D mole